Hi, my name is Michelle Hitu and I'm an applications engineer at Hanna Instruments. Today, we're going to be going over the principles of titration and performing a manual titration. Titrations are used in a wide variety of industries, including municipal water, wastewater, food and beverage, wine, pharmacy, plating, and more. A titration is an analytical procedure in which an unknown concentration in a sample, called the analyte, is determined by reacting it quantitatively with a substance of known concentration called our titrant. Titrant is added to the sample until the reaction with the analyte goes to completion. This is called the titration endpoint. This endpoint can be determined using a color indicator or potentiometrically. Today, we're going to be determining the acidity of orange juice using a sodium hydroxide titrant, using both a color indicator and a pH electrode and meter to determine our endpoint. To perform a manual titration, we'll need the following equipment: a burette and ring stand, our titrant, which today is HI7046 0.1 normal sodium hydroxide, a stirrer and stir bar, such as our HI190M, a pH meter, such as our HI3222 research grade meter, a pH electrode, such as our HI1131B, an automatic temperature compensation probe, and a color indicator. Today we'll be using phenolphthalein, which changes from colorless to pale pink at a pH of approximately 8.2. For the determination of percent citric acid in orange juice today, we'll be using a 10 milliliter sample which we obtained volumetrically and diluted with distilled water. We're going to be examining the two most commonly used methods for endpoint determination in a manual titration. These are potentiometrically with a pH electrode and pH meter, and using a color indicator, which today is phenolphthalein. This method has an endpoint of pH 8.2, which coincides with the point that phenolphthalein changes from a colorless liquid to a pale pink. Reading our meniscus, we record that our starting volume for titrant is 11.62 milliliters. Once we have our sample stirring, we add 4 drops of our color indicator phenolphthalein. We immerse our temperature probe and our pH electrode in the solution, making sure the reference junction is submerged. We observe that our starting pH is just above 4. Now, we can open the stopcock and begin dosing our titrant in the sample. Initially, as we add our titrant, we see that the solution remains colorless with each titrant dose, and our pH is changing relatively slowly, only in the hundredths for every drop added. As we get closer to the endpoint, we're seeing that the colors begin to flash in the solution, but the color change is not sustained, indicating that we aren't yet at the endpoint. Our pH begins to change more quickly with every titrant dose. At this point, we're going to begin to add smaller doses and wait for each titrant dose to completely react with the analyte before adding another dose. By doing this, we ensure that we're accurately detecting our endpoint and not overshooting it. As we can see, the pale pink color in our solution is sustained, and our pH has become stable right about 8.2. You may have noticed that the color change is slightly hard to see, especially because of the colored matrix of the orange juice. This is where having a pH electrode and pH meter instead can be an advantage. I just want to show you that if we dose additional titrant and we go past our endpoint, our pH begins to change again and our color becomes very vibrant. If a titration gets to this point, the endpoint has been overshot and our concentration of our analyte would be overestimated. Once we've reached our endpoint, we record our final titrant volume to be 21.28 milliliters. By determining the difference between our starting and final titrant volumes, we determined that 9.66 milliliters of titrant was used to reach the titration endpoint. If we go back to our titration equation, we can look at our variables, which are 9.66 milliliters, our volume of titrant used, multiplied by 0.1 normal sodium hydroxide, which is our titrant strength, our reaction ratio of 1 mole of citric acid to 3 moles of sodium hydroxide, our molecular weight of citric acid, which is 192.12, over our conversion factor of 10, and our sample size, which is 10 milliliters. When we run this equation, we get a result of 0.618 grams of citric acid per 100 milliliters of orange juice. In addition to pH meters and electrodes for manual titration, Hannah also manufactures automatic titration systems, including our research-grade potentiometric titrator, the HI902C, as well as an industry-specific line of mini titrators, which includes the HI84432, the mini titrator for acidity in fruit juice. And that's how you measure citric acid in orange juice using a manual titration. When looking at these two methods for endpoint determination via titration, we can see that each method has some strengths and some weaknesses. Color indicators, such as phenolphthalein, which we use today, are low cost, low technology, and easy to use, but the initial color change can be hard to see, especially in colored liquids such as orange juice. Also, everyone perceives colors differently, so getting repeatability among many users is difficult. This method is moderately accurate. A pH meter and electrode is a little more expensive and requires some knowledge of technology, but there is no subjectivity when the reading. The 8.2 endpoint is easy to detect among many users, so results are highly accurate and highly repeatable. If you have any more questions about titration, please visit www.hannahinst.com.